Well, thank you. Hello, and welcome back to Calculus1, section 3.7 again. So, part 2. We're talking about the chain rule. What we have done so far is reviewed pre-calculus function composition, talked about the skill of decomposing functions, which is actually what we need, and then we did a lot of examples for the chain rule. Now, one of the main focuses of chapter 3 and calculus 1 is to compute the tangent line, because the slope of the tangent line measures instantaneous change. Last class we said that slope, the derivative measures, which is the slope of the line, measures instantaneous change, which is instantaneous velocity, which is the speed at which you're going at every time. At any time. And then we also talked about marginal cost. I did talk about change of population at the end of the class and so on. So now we would like to find the tangent line. Now, tangent line requires you to find the derivative and then plug the value in, and then when you do that, you calculate the slope, then you find the b, and you're done. Now, to find that derivative, right, it could be basic, it could be product rule, could be quotient rule, or could be chain rule, right? So let's have an example for the tangent line where you are supposed to calculate the equation of the tangent line given the chain rule as your function. So this is problem 95 in the textbook. It says, find tangent line for y equals e to the 2x at x equals 1/2 ln 3. Now we see that the function has e to the x of some form, and then of some form, and then we see ln 3, so that's great because it's easy to compute in that case. So our job is to find the derivative. So f prime of x would be the derivative of e to the 2x, which is the chain rule, right? Your function is e to the x, your g is 2x. Now you did memorize this before with a, so you know that the answer is 2 e to the 2x, but you can actually use the chain rule and not worry about the a formula anymore, because now you know that the derivative of e to the x is still itself e to the x, and you copy 2x instead of x, and then derivative of 2x is 2, which is the number in front. Now slope m is going to be the derivative computed at the point of interest, which is 1/2 ln 3. So 2 times e to the 2 times 1/2 ln 3, and that's 2 times e to the ln 3, which is 2 times 3, which is 6. The y function is the original function computed at the point of interest, which is 1/2 ln 3, and that's e to the 2 times 1/2 ln 3, which is e to the ln 3, which is 3. So I have everything. I have that m is equal to 6, and the point is 1/2 ln 3, 3. So now we plug everything into y equal mx plus b. If you like the other formula, you can use that. Y minus y1 equals m times x minus x1. Y is 3, m is 6, x is 1/2 ln 3 plus b. These cancel. So b is equal to 3 minus 3 ln 3. And we're done. Y equals 6x plus 3 minus 3 ln 3. You can actually compute this as a decimal, and you would have it in a form y equal mx plus b. I'm going to leave it this way because this is the exact answer. So we can find the tangent line by using chain rule as well. So the last couple of problems for today will be devoted to this mixture of different rules. So far, all we had was pure chain rule. You only had to worry about the chain rule, you complete the chain rule, and you're done. But most of the functions we deal with are not just chain rule. They are not most, some of the functions are more than that. So say you have three x.
Just the chain rule to solve them?
Yeah, more than just chain. So let's say you're looking for the derivative of 3x plus 1 to the 6th power times e to the x squared. What would this be?
Oh boy.
What is the first thing that you can see? Yes?
Is it product rule?
Product rule. Beautiful. We have function f, we have function g, which are multiplied. So this problem is a product rule. But if you take a look at each one of these individually, each one is a chain rule, right? So every time when you're copying these, right, in a product rule you copy g once, you copy f once. But every time when you're copying these, you just copy them. But when you have to take derivatives, you have to use the chain rule to take derivatives. So we know that the product rule formula was fg prime plus gf prime. That was a good effort right there. So we copy f, which is 3x plus 1 to the 6th power. And now we are supposed to take derivative of g. Well, that's a chain rule. The derivative of e to the something is e to that something times the derivative of the exponent, which is 2x. So this is my copy f, and this is my g prime for product rule. Then we have a plus, and then we have copy g. Well, that's e to the x squared, and then times the derivative of f. Well, that's another chain rule of 6 3x plus 1 to the 5th power times the derivative of the inside, which is 3. And all you need to do is to clean it up. and then factor it at the end. And now, in chapter 4, set it equal to 0 and solve each one to get critical points, and then do the first derivative test, you know, which one is made. That's chapter 4. It's written right there.
This is supposed to be the product rule.
Yes. Do the product rule, C by F and G prime and G F prime.
Oh.
And then I did algebra after that. So, all right. So for factoring over here, we have 2 that is in common between 2 and 18. We have 5 of these 3x plus 1 that go in a pile, and e to the x squared that goes in a pile. The leftovers are a single x, 3x plus 1 from the first, and then from the second one only 9 as leftover. And you multiply that and add that together, and that's it. So this is the way to deal with the composite, right? Oh, sorry, with multiple rules. So we have 2 composite functions multiplied, so we have a product rule.
So how does the 2x become separate from the x squared?
What do you mean separate?
So you have-
You mean this 2x?
Yes.
It's a chain rule. Chain rule.
That's going to be 2x. Why is the x squared still there?
You always copy the original function for derivative of e to the x. Derivative of sine is cosine, derivative of e to the x is e to the x. So you would still copy e to the, like e to the g. I think we had a problem like that before, somewhere.
Why not e over 2x then?
There it is. The exponent stays, and then you have the derivative of the exponent. Yeah. When you do a few examples, it will make sense, but we can always talk more about it. Let's take a look at another example you are going to love to hate. How about x squared plus 3 divided by sine x, everything raised to the 6th power. Which rules are we talking about here? And
Quotient rule
and chain rule. Good.
chain rule. Yes.
Now, which one is the boss, the main rule?
Chain, the quotient. Yeah, that. Chain rule. That's the quotient. Okay. Well, what do we do with
Chain rule or quotient rule?
quotient rule? Chain rule.
Oh,
There's
no,
a
it's the
six
chain
around.
rule.
It is the chain rule, yes.
There's a 6 all around it.
6 is all around it. You see? It's not signed to the 6.
That's it.
It is everything to the 6th power. So chain rule is the boss.
Put a 6.
Quotient is inside
coefficient,
this time.
And the exponent will become 5, right?
Yes. So now, this entire problem looks like a big fat X to the 6th power. That's what it looks like. The entire problem. Would you agree? Yeah, right? So the solution to this must be 6x to the 5. But x is actually this mess. And then we have to do the chain, which is when quotient kicks in. So we start with 6 x squared plus 3 over sine x to the 5th. That's where we start. Times, you okay with it?
Yep.
Times, and now we do the quotient. We take sine and square it. We put the sine x. Derivative of the numerator is 2x minus x squared plus 3, and derivative of sine is cosine x. And just walk away. Yes.
I just want to say, I took calc in high school, and she taught it by saying low d high minus high d low over the square of what's below. If you have trouble memorizing.
I don't, but that might be very helpful for.
Yeah.
Would you like to perform it or no? Can you say it louder so everyone can hear?
Low d high minus high d low over the square of what's below.
So this would be high, this would be low,
Yeah.
and it also is below. Okay. So
Low.
Low.
It's like low.
Low.
Denominator. D high, so like the derivative of the numerator, minus high, so the numerator. D low, the derivative of the denominator, over the square of what's below. So the square of the denominator. Yeah. Yeah. That's just.
that's called calculus poetry, right? Well, thank you for that insight. So low d high minus high d low over the square root of what's below. They should add that. Great. One more example and that's it, right?
Remind me, is sine x squared minus cosine x squared, is that negative 1?
No, that's negative cosine 2x.
Right.
You're so happy.
I have to think about that.
About what?
The answer to that question.
The high, the low, I never...
No, the trig one.
Sine square minus cosine square? Yeah, because cosine squared minus sine squared is 1. No, it's not 1, it's cosine 2x. So if you swap them, you just get the minus, yeah.
That's a 5.
Well, pick one from the homework.
So this can't be simplified any further?
It can, but there is no reason. What's the derivative of, this is problem 50, x over e3 to the x?
Is that e to the 3x power or e to the 3 to the x power?
E to the 3x. So what is the main rule? Quotient rule. Are you singing it again or no?
I think in my head, yeah.
So we have e to the 6x, e to the 3x times 1 minus x 3e to the 3x. we factor out e to the 3x and have 1 minus 3x divided by, we can make this 6x as 3x plus 3x, so e to the 3x times e to the 3x, and then 1 will cancel to give us this awesome result. I hope you'll do 5,000 of these examples, and then we'll do some tomorrow. See you tomorrow.